Okay. Let's see. Moment of panic at the first moment I get up. Okay, that's over. I've spoken here before about the MOTESS instrument. Many of you probably remember it, but I'm sure there's some new people here. So just a quick refresher. Okay. Oh, it's the big one. Okay, there we go. The MOTESS instrument is an array of three 14-inch aperture telescopes, Newtonian type configuration, f5. Each one has a 1K square CCD camera at the focus. The instruments operate in scan mode from evening twilight until morning twilight, imaging a continuous strip of sky all night. The field is 0.8 of a degree wide, and the typical coverage in the course of a night, 120 to 180 square degrees, depending upon the season. The telescopes are spread apart in right ascension. They're all the same declination, but spread apart in right ascension so that objects that drift through the fields of view do so with separations of about 20 minutes of time. The original mission of the instrument was to look for moving objects, asteroids, comets, whatever, in particular near-Earth asteroids. The instrument penetrates down to about magnitude 20.5. The total field of view in the course of a year is 288 square degrees. That's the entire circle around the sky. The data were archived, the imagery data was archived, and the idea being that is after you've looked for the asteroids, the moving stuff, you could then use the images for looking for variable stars, who knows, whatever else. It serves as a nice record for what appeared in the sky during that period of time. It was decided to operate the instrument as 2-year surveys, look at the same strip for a couple of years, go to a different declination, and resume operations. And let's see, there we go. The instrument began operating in 2001 and continued until about 2011 in its primary role of looking for asteroids. The professional surveys became so good that any asteroids that I was seeing was usually a few days after some professional survey had found it. So it was decided to shift the focus from moving objects to variable stars. And that's been a surprisingly productive and very exciting type of activity. Let's see. The variable star catalog, the first MG1 variable star catalog, I indicate here it can be found at enat.org, but the website has been hacked quite a bit in recent times. Apparently hackers get on there and post links to other websites with other heavenly bodies. So if you want to examine the catalog, you can go to Vizier, and the entire catalog is available there, along with various search routines that will permit you to look for the sorts of objects you're looking for. There's a couple of things to be aware of when you look at this catalog and search for interesting objects to observe. Although the surveys were accomplished with 3 telescopes, in this particular one, the first survey, we used only 2 telescopes. So the statistics are not quite as good as later when we were using all 3 telescopes. And remember, the sampling interval between each observation is exactly 1 sidereal day. The telescopes never moved around except when we were pointing between surveys. It's a very simple operation. You start the telescopes in the evening, turn them off in the morning, and all night they just sit there like big pet rocks. They don't move around at all. So there's a 1 sidereal day sampling interval between all the observations. Now, if you've got objects with periods of variability shorter than a day, the light curve information is hopelessly aliased. The entries in the variable star tables have an automatic routine tried to come up with a light curve from the data. But if the object actually has a short period of variation, less than a day or so, it's just an advisory sort of light curve. It'll give you an idea of the sort of shape of the light curve, but don't attribute any sort of accuracy to the period. And there's some statistics associated with each of the table entries. If you look at the table, we'll do that in just a moment, you'll see there's an object designation, right ascension, declination. There's an R magnitude. The telescopes were operated unfiltered for the survey data, but the response of the CCDs is sort of approximately Johnson R, to give you an idea. The amplitude of the variation listed in the table, the standard deviation, which is sort of gives you an idea of the brightness of the object, because there's a certain noisiness that increases as the objects become fainter. We indicate a photometric error associated with that. Then there is a skew. Instead of a nice Gaussian sort of statistics, things might be shifted one way or the other depending upon the type of object. For example, a eclipsing binary will show predominantly one main region of brightness, but then there'll be a tail off towards the fainter end, where we may have recorded the object in eclipse. So this skew can sometimes be interpreted as what type of object, or sometimes you'll see when you look at actually the photometry graph, you'll see that the values of the photometry seem to be bimodal. It's sort of like half bright, half faint, and that sort of suggests something with a sinusoidal variation in light. There is an indication of the total number of observations in the catalog. There is a log of the period of variation, which if it's less than a day, it's totally bogus. And then there is a log of the probability that it's a false alarm about periodic behavior. Some of these objects are real scattergrams. There's no periodic indication at all. It's just randomly varying. Let's, for example, look at the table entries here. Again, designation RA dec, brightness, amplitude, and then we get to log period, and all of the periods are going to be computed to be at least a day, simply because that's the sampling period. More about that in just a moment. The log probability of false alarm. The software did a process to see if it's likely that it was a real variation, periodic in nature, or if there's no real periodic. I won't get into the details, but this is an advisory number. If you see a large negative number, you can have a high degree of confidence that it really is a periodically varying object. For a small number, 0 point something or other, that very likely is some kind of real random variation. Then there's a couple of entries there where you can get the photometry data. You can't do that right now unless you go to Vizier. And then there's a light curve button, that a link, and it'll bring up the graphical representation. The top half is the actual data, and below that was an attempt to display a light curve. Now, this is sort of an example. The top is a reconstructed light curve. The bottom is the actual photometry data. Now, what's wrong with this? You'll see that at the top of the top plot, there's a single point. This is an ERALF, flare backwards. One thing to be aware of, is that the photometry plots are inverted compared to the usual sense. The plotting routines were plotted with numbers increasing towards the top. Well, in astronomy, we know as the numbers get bigger, it actually gets fainter. So be aware that the faint direction is towards the top. So this is an example of something that probably should have been culled out before inclusion into the tabular data, but we didn't. So this is one of those things to be aware of. If you think you got something interesting, always be sure to look at the photometry plot. This is an object that has high amplitude but low standard deviation. So in other words, it's a relatively constant object with an outlier some distance away, and we know that's kind of bogus. Now this is something that's real. This is an object that has a multi-day period, so the software routines worked very well to try and give you an idea of the light curve. Now, one thing to look at in multi-day, long period varying objects is if you look at the lower left plot, you'll see some sort of vertical structure. That's usually an indication that these are this is a plot of the brightness versus time, and so this is a slowly varying object, and you're actually getting sort of miniature little light curves, giving the impression of these vertical stripes. So if you're just quickly looking at some photometry plots, that's what you would look for something that's long period, like a Cepheid or semi-regular or something like that. And the software did a fairly good job coming up with something that looks like a real light curve. Well, let's compare what the software routines did with something with a relatively short period. Now on the left is the photometry plot. You can see towards the bottom, this is what I would call sort of a bimodal distribution. You see there's an increased density towards the top and the bottom of the plot, but otherwise it's a scattered diagram. It tried to construct a light curve. There was enough aliased periodicity that it successfully concocted a light curve, and I call it sort of a bouncing ball type light curve, which is usually an indication that it's a very short period ellipsoidal or eclipsing binary. And on the right side, the software program Paranzo was used to concoct a distribution of proposed periods versus the degree to which they correlated. And it's difficult, this is less than a day. This was a range of 5 to 12 hours, much less than a day, and it made hopelessly no sense at all as to what the actual period was. I can tell you right now it's about 7.42 hours, and this is actual follow-up data. Again, the answer was 7.5 hours from this data. Once I have a night's worth or a few nights worth of data where I can unambiguously indicate what the neighborhood of the period is, I can then go back to the original MG1 catalog data, which has a period of 2 years. I can plug in the approximate range of the period, and out comes a very precise indication of the period. So I came up with 7.5 hours from the follow-up data, and then going back to the MG1 data, I got a very precise 7.42296 hours. So the two data sets complement each other very nicely. Now, let's do the same thing with this guy. It's a pulsator, obviously, sinusoidal sort of waveform. Maybe it's an RR Lyrae, but this is what I got from a few nights follow-up observations, and I got, on the order of like 9 hours. But if I plug that into, if I take the MG1 data and plug it in, it comes up with a 9.04533, somewhat different from the period I got with the follow-up data. Gee, that's odd. Why can't I get a nice, pretty light curve? This is the best I could do. Well, if I take the MG1 data and I force upon it the same period that I got with the follow-up, I get this. I get two pretty overlapped, superimposed waveforms. In other words, it really is is a strictly periodic object, but something happens so that it shifts phase once in a while, apparently. It's one of those, when we were starting to do follow-up, we would get just enough to get an unambiguous period that we could use with the original MG1 data, and then we would go into the next object. It was only later when we began to look at stuff in detail that we began to notice things were changing. Like, for example, this guy. On the left side, this is the first year of the 2-year survey, and you can see an eclipsing object, but the minima are almost the same. On the right, a year later, you can see that it's become different. And this is the follow-up data. Now the difference between the minima is on the order of 0.3 of a magnitude. We're actually seeing this object evolve with remarkable speed. I guess we were just lucky, except this is another such object. Apparently this sort of behavior we come across more commonly than we would have expected. I don't know if it's precession of the plane of orbit induced by a third object or something like that, but we're beginning to see that variable objects are varying in their variability with time, sometimes with remarkable speed. And another exciting thing, star spots. This is something that just cries out to be for real follow-up. You can think of all sorts of things. Colors, variability of the change in the waveforms of time. This is something I'm really looking forward to spending more time on these sorts of objects. So the message here is that these MOTESS-GNAT surveys are a rich source of interesting things to look at. Each survey produces some 20,000 variable star candidates. We've only looked at a couple of hundred of them so far, and we've got 4 more surveys that we're getting ready to process now. So if you're looking for variable stars to look at, I think we can come up with some really exciting things. Now, I haven't mentioned the really exciting ones that we're keeping under our hats for some future meeting. So these are just sort of the ordinary, middle-of-the-road exciting objects that I've mentioned here. So if anybody wants to get interested, help us follow up variable stars, we'd be happy to have you get involved with us. Thank you very much. Any questions? Sir. Oh, yes. Oh, yes. One of our collaborators, Adam Krause, is a professional astronomer who has published some papers based upon the M-dwarf eclipsing binaries to be found in our data. Before we started this survey, there were only 6 known M-dwarf eclipsing binaries. Now, you'll know that eclipsing binaries are vitally important for precisely defining the characteristics of stars and for placing it somewhere on the Hertzsprung-Russell diagram. M-dwarfs are very faint intrinsically objects, and you can't see them a long ways off. So it's hard to find M-dwarfs, and it's really tough to find ones that are eclipsing binaries. And this first survey has yielded 30 such systems, and we've published papers based upon that. So yeah, this is indeed exciting stuff, and it was kind of neat. I kind of came across one in M-dwarf eclipsing binary in an object that was following up. I reported it to Adam, and the very next night he was looking at it with Keck, so that was kind of a thrill. Anything else?
Time for one more? Anyone?
Get with me after the
thank you very much.
Thank you very much.
Wait a minute.